Have you ever wondered why self-driving fails, or why long-endurance UAVs, high-speed rail inspection vehicles, and unmanned mining equipment can maintain precise positioning even in extreme environments? Behind all of them, there is actually an invisible heart. It doesn't emit light or heat, but once it fails, the entire system instantly loses its sense of direction. This is the high-precision IMU, or inertial measurement unit. Unlike the sensors in your phone that cost just a few dozen yuan, high-end IMUs are hundreds or even thousands of times more accurate. They need to operate reliably in environments ranging from minus 40 degrees Celsius to extreme heat. With a lifespan of over 10 years, they can even maintain precise navigation when GPS is completely unavailable. So here's the question. How is a truly industrial grade, tactical grade, or even navigation grade IMU actually made? Today, we'll take you through the entire process. The entire process from conceptual design to mass delivery. Once the requirements are determined, we move on to the second stage, architecture design. At this point, engineers begin to answer a practical question. What will this thing actually look like? There are usually two approaches. The first is the modular IMU, which integrates the MEMS, MCU, power management, and temperature sensor all onto a single board. This is the most common solution for industrial-grade products. The second, more advanced type is the system-level IMU. It not only outputs raw data, but also directly provides attitude, velocity, and position, and may even have already performed sensor fusion for you. This is commonly found in tactical grade and even navigation grade devices. At the same time, the engineering team also needs to start working on the error budget. Upon reaching the third stage, the truly expensive part begins. If you are pursuing the MEMS route, this entails wafer fabrication, that is, processing micron-scale structures onto silicon wafers. Through deep reactive ion etching, specifically the DRIE process, tiny proof masses and flexural beams are sculpted. Subsequently, vacuum packaging is performed to ensure the system maintains high stability. However, many people are unaware that what truly determines the performance is not the MEMS device itself alone. There is another key player. ASIC chips. Since MEMS sensors produce extremely faint signals without high-quality ASIC amplification, filtering, and compensation, even the most expensive MEMS device cannot operate stably. However, if one takes a different approach, fiber optic gyroscopes, the process becomes even more complex. Engineers must precisely wind polarization maintaining fibers coil upon coil while controlling tension, thermal drift, and polarization errors. Only then can they complete the optical splicing. Error control, carried out with a precision extending even to a loss level of 0.05 dB. Many people think that hardware design is just about drawing PCBs, but for high-end IMUs, the PCB is more like a battlefield in a war against interference. Engineers must solve three problems. First, mechanical stress, because even a slight deformation can cause measurement errors. Second, thermal management. High-end products even actively control the thermal gradient to maintain a constant temperature. Third, low-noise design, including differential routing, power isolation, and magnetic shielding walls. Every detail serves the same purpose, to keep the signal as clean as possible. For fiber optic gyroscope IMUs, the fiber ring even requires its own temperature control because temperature changes can affect the final navigation accuracy. When it comes to the packaging stage, the difficulty increases once again. This is because high-end MEMS devices are extremely sensitive to stress. If the packaging is even slightly off, their performance will collapse completely. That's why industrial-grade products commonly use ceramic packaging, a metal housing, and low-stress materials. The interior is even evacuated. A fiber optic gyroscope, however, is more akin to constructing a miniature optical laboratory. The light source, detector, and Y-waveguide are all hermetically sealed within a metal module. Then hermetic sealing is completed in a clean environment to prevent any dust from entering. Many people think that hardware determines everything, but that's not entirely true, because what truly determines the upper limit is the algorithm. Software is usually divided into 3 layers. The first layer is drivers and communication, responsible for reading sensor data. The second layer compensates for errors, addressing issues like zero bias, temperature drift, and misalignment, because each MEMS device has individual differences. Therefore, it's necessary to establish your own compensation model. The third layer, which is also the most complex, is the integrated navigation algorithm, such as the extended Kalman filter. It fuses data from the gyroscope, accelerometer, GNSS, magnetometer, and odometer to produce the final output. Attitude, velocity, and position. In many cases, what actually generates revenue isn't the hardware, but this layer. Finally, we come to the most painful stage of the entire project, testing and calibration, which is also the most expensive step. Because truly high-end IMUs are not just manufactured, they are fine-tuned through calibration. They must undergo static testing at extreme temperatures, full temperature range calibration, random noise testing, as well as vibration and shock testing. Aging and reliability screening are also required. Some products need to be repeatedly tested at tens of thousands of data points between -30, -40 degrees, up to 120 degrees Celsius. In the end, the compensation parameters for each sensor are written into the chip, and sometimes even full functional certification is completed. From initial design to actual mass delivery, a moderately complex project often takes 2 to 4 years. So, a high-end IMU is far more than just a sensor. It is a comprehensive system engineering project involving materials, chip manufacturing, hardware, algorithms, testing, and certification. The process includes requirements definition, architecture design, core component manufacturing, hardware design, packaging and assembly, software algorithms, calibration and testing, inspection, and mass production delivery. This path consumes money, time, and talent. But once you break through, it also means truly entering the high-precision inertial navigation industry chain.